All right, so we've seen this limit formula interpreted a couple different ways so far, right? We know that if we take the limit as h approaches 0, and we do f of a plus h minus f of a all over h, what we're really doing is finding the instantaneous rate of change. Or we also just talked about in the last video that using this formula will also help us find the slope of a function at a certain point, or we called it the slope of the tangent line. Well, this formula also can be interpreted and used to calculate rate of change in any situation. For example, rate of a reaction in chemistry or marginal cost in economics, how the cost is changing. And since this type of limit occurs so often, we give it a special name and a special notation. We're going to now call it the derivative. So you might have heard that word before, the derivative in calculus. Well, that's what this is. We can find the derivative by applying this limit definition. And we can find the derivative at any x value. So maybe we don't know what x value we want to find the instantaneous rate of change is. So instead of plugging in a value for a, we can actually just use x and find the derivative or the instantaneous rate of change or the slope of any tangent line at any x value by using this formula and plugging in an x plus h and then an x. Now there's also a special notation we use for derivative now. It looks kind of like this. Well, there's actually a couple different notations that we can use, but one of the most popular looks like this. We say f prime of x. That's the derivative, the instantaneous rate of change or the slope of the tangent line. Another notation that you might see is dy over dx. That's the derivative of y with respect to x. Or you might say y prime. Or you might say d of f of x dx. That's the derivative of your function with respect to x. So a couple of different notations you might see. Make sure that you're comfortable with whatever notation they give you. They all just mean that we're going to use this limit idea to find the instantaneous rate of change, the slope of the tangent line, or the slope at one point, the derivative. So one more time, there's a couple of different interpretations for that formula. We can say that that's the derivative now, or we can say that that's the instantaneous rate of change, how something is changing at that exact moment. We can say that it's the slope of the tangent line at that point, or we can really say that it's a slope at any one point, right? And so we've talked about the difference between the difference quotient, an average rate of change, or just finding the slope between 2 points, right? Slope of a secant line, average rate of change, average velocity, average. As soon as we hear that word average, we know we're just doing the slope between 2 points. But if we apply that limit idea and we make h go to 0, remember we're taking those 2 points and moving them so close together, eventually it's just 1 point. We're finding really the slope of the tangent line, or the instantaneous rate of change, or the instantaneous velocity, or when we start to talk about some business examples, economic examples, we might hear the words marginal cost. That's the rate at which the cost is changing at a certain point. Or the marginal revenue. How is your revenue changing at a certain point? Or maybe even marginal profit. How is your profit changing at that moment? So we're going to do a few examples of that in a little bit. All right, let's go ahead and for right now, find the derivative. So again, remember finding the derivative is doing what we've been doing so far with the limit as h approaches 0. But now if you notice in example number 2, it gives us a function, f of x equals x squared, and it asks us to find the derivative. But it doesn't say find the derivative at a specific number. So what we're going to do is we're going to find the derivative at any x value. So when we do our limit formula, and we do the limit as h approaches 0 of f of, instead of putting a number there, we're going to put an x plus h minus f of x all over h. And so what we're doing here is we're finding the derivative at any x value. What we have to do now is then wherever I see a variable in my function, I'm going to plug in an x plus h, just like we did before. And then I'm going to plug in my f of x. So if my function is x squared, as soon as I see that variable, the x, I'm going to substitute in an x plus h. So f of x plus h in this problem is really x plus h squared, the x squared, right? Minus f of x. Well, f of x is equal to x squared, so that's where I plugged that in. So I plugged in my x plus h, and I plugged in an x. From here, we just have to simplify. We've got to FOIL, combine like terms, and see if we can apply that limit as h approaches 0. So make sure, whoops, I didn't want to erase it. Make sure you FOIL this part here, x plus h times another x plus h. Combine your like terms, and don't forget to subtract an x squared from the back. When I did that, my positive x squared and my negative x squared cancel. Remember, anything without an h should, right? So then we can factor out an h. I have left over then a 2x plus h all over h. Our h in the numerator and our h in the denominator should reduce, and so now I can apply the limit as h approaches 0. I can smush these 2 points so close together so that we're finding the derivative or the instantaneous rate of change or the slope of the tangent line. Let's plug in 0 here and see what we get. When I plug in 0, I end up getting 2x plus 0, which really means that the derivative is just 2x. So I can say that my derivative is 2x, f prime of x is 2x. I can say that my instantaneous rate of change at any x value is 2 times x. I could say that the slope of my tangent line at any x value is also 2x. So lots of different interpretations for the same thing. So if you look at Part B then asks us to calculate and interpret f prime of 3. So this little notation here is really important. I don't want to take 3 and plug it into my original f. I want to take 3 and plug it into my derivative. I want to find the derivative's value when x equals 3. Or I want to find the instantaneous rate of change at exactly x equals 3. Or I want to find the slope of the tangent line that touches at x equals 3. All of those different things mean the same thing. If I plug in a 3 into my derivative, remember it was 2 times x, I have 2 times 3, which is really 6. So that means my instantaneous rate of change when x is 3 is 6. Or the slope of my tangent line when it touches at x equals 3 is 6. My derivative is 6. All different interpretations using that same limit idea. We'll do some more example problems here in the next videos.